So let's actually prove this. I'm going to go ahead and prove the slightly stronger statement. We're going to show that for all positive integers n, we're not going to start with 0, we're going to start with 1. 7 to the n minus 2 to the n is not only divisible by 5, but it really is always an odd multiple of 5. So that pattern that we were seeing, that it really ends in 5, in other words, is really going to be true. Okay, so I want to introduce some careful terminology that's really helpful when you learn induction, when you think about the logic of induction. The whole point here is that we're trying to generalize to an infinite number of statements and an infinite number of mathematical propositions, and we need to be careful about that. So we're going to say P of K, or in general P of K or something like that, is a proposition. So P of 1 is the claim that that 7 to the 1 minus 2 to the 1 is an odd multiple of 5. Now that's clearly true. It's 5, so, but I wanted to get the terminology out mainly more than just to figure out what's true and what's not. P of 2 is the claim that when I put in n equals 2, 7 to the 2 minus 2 to the 2 is an odd multiple of 5, etc. P of K is the statement that 7 to the K minus 2 to the K is an odd multiple of 5. And the reason I wanted to have labels for that, and the reason the book has labels for that, is to make clear the logical structure of an induction argument. There's two pieces to it. There's the base case and the inductive step. The base case is usually simple and quick, but is crucial. And then the inductive step is where the interesting stuff happens. Okay. The base case here is simply to check that the starting proposition is true. Check P of 1 is true. And that's obvious because that is equal to 5. Okay, so we can consider that checked. The inductive step, let me lay out the idea of the inductive step. Oop, I erased our to show, but that's okay, we don't have that much room. And then in the next video, we'll actually look at the algebra that does it. The inductive step is always of the form that we show that if the thing we want to prove is true for case K, then it's true for case K plus 1. And let me be a little bit more careful about that. It's really show that for every positive integer K, if P of K is true, then P of K plus 1 is true. Why does that accomplish what we want to accomplish? Well, intuitively at least, if we know P of 1 is true, which we do, that was the base case, then we can apply this. Okay, we know that no matter what integer we have, K, if I happen to know that P of K is true, then I can get to the next statement. Well, I do know P of 1 is true, and therefore P of 2 is going to be true. Okay, now I apply this where K is 2. I happen to now know that P of 2 is true, and now I can use that to show that P of 3 is true. And then that shows that P of 4 is true, and it never stops. And that's the big thing. That's where infinity kind of comes in here in a very, very basic way in mathematics, that we can assert that this is never going to stop, that it's going to be true for all positive integers. The way I like to say it is often just practically, suppose somebody checked that 7 to the 231 minus 2 to the 231 is an odd multiple of K, odd multiple of 5. Is there an easy way to check, if we trust that calculation, is there an easy way to check that the same is true for 232? And I'll show you that there is an easy way. If that's true, then this is good. We're going to trust that somebody did it for 231, and then we're going to know it's true for 232. But why should we trust that it's true for 231? Maybe he's faking it. Maybe he didn't do this calculation. Well, he heard it from a friend that it was true for 230, and then he carefully showed that if he was sure that it was true for 230, it was true for 231. And we carefully showed that if it's true for 231, it's true for 232. Well, how do we know it's true for 230? Well, if you can unravel that back all the way to 1, and we know it's true for 1, then it really is okay. And then you can go forward as well. So, practically speaking, what we're going to need to do is have a connection between a statement like this, the divisibility of this guy, and the divisibility of the previous one. There's lots of places where that's hard, and you just get stuck, and an inductive argument isn't going to work. But we're going to see that because of the nature of powers, of exponents, it's going to be not too hard to relate those two together. And that's what we'll do in the next part.